Let me get your CD. Real time. Yeah, Doctor, as he graduated from Queensland University in Australia, and I think he used to work in the Australia. What is your research center?
Yeah, it's called CSR, or maybe skip that part. Yeah. So basically it's a National Research Lab.
Yeah, something to do with bioinformatics, if I understand correctly. And I think one thing I like highlight you have many awards, right? And one of these is something to do with soccer. You know, want to tell a bit about.
Okay, if we've got time, we'll go to the soccer video. It was a visualization of the history of the World Cup. So which team win the most, what the general structures of the team winning, over the whole history, and that was for competition. So we won some awards there. But if we have time, we'll go there. And
okay, yeah. Please tell us about what is visual analytics.
Yeah.
How you can actually do that.
Okay, so thanks for introduction. And exactly, so this talk is try to tell you some kind of emerging new field called visual analytics. And really, I try to cover lots of things in one talk, so it wouldn't really go into depth at all. But hopefully I can get across the concept of visual analytics and what it is, and why it's important, exciting, or useful, and what are the problems there that you might want to look at a bit further. Okay, let's start. So that's an outline. I'll do a kind of gentle introductions with lots of pictures, so keep you awake. And then, so we'll talk about visual analytics and data management. And visual analytics itself is kind of an intersection of many different fields, and we'll see later on. And I picked the two fields which is most relevant, I think, to information retrieval, which is I thought was the core or the focus of this course. So first one I picked is data management, and the second one is data mining. And so we'll look at a little bit more details of the existing work in those two fields, involve both visual analytics and data mining and data management. And finally, if you've got time, we're going to do some demo of the system we developed, and we'll be able to show you how it works in real time. And if we still got time after that, we'll have a look at the World Cup video. Okay, so I'll start with introducing the visual analytics. And I start with a little bit of background. And how many of you heard of big data? Oh, very good. So I probably can skip all these slides altogether. Anyway, and also last speakers, and I think touched on the topic anyway. So he gave a very good, real life example of how people is dealing with big data. So if you go it's quite difficult. I mean, the definition. One of the definitions is and the size of the data had to be beyond the ability of the typical database software, so based on a relational model, and really depends on task. And sometimes a few dozen terabytes is already too big, sometimes that goes to level of petabytes, etc. So we look at examples of Twitter, 340 million tweets a day, and actually this is something I'm particularly interested in. One of the demos is about how to analyze Twitter data visually. And Facebook claim they have 4 billion shared things per day and 500 terabytes data per day. And this is some number from the McKinsey Institute. So this is the consulting institute, and which I think we mentioned before. So they did some wild estimation, say in 2010 with 7 exabytes. So 1 exabyte is 1 million terabytes. So that's the total globally. And so from same institute, the McKinsey, they did a study, that's what they do, and they studied the business values of understanding big data. So they say there's 300 billion values to the US healthcare alone every year. So that's really a lot of money. Okay, so the next challenge is to understand the big data. And I think from the last talk, we already get impressions say it's actually very difficult. And how do you actually make your analysis scale up with the data size? So I personally think it will be very difficult to use computational alone. Okay, so So the argument I put here is saying most non-trivial, trivial analysis require more than linear running time. And would you agree with me on that? Say, for example, the simplest one you can do is sorting, and that takes more than linear time to do a sorting in real world. And if we assume the data grows exponential, and then you need more than linear time to cope with that, then say the computational power needs to increase at speed of exponential, or maybe say the quadratic exponential, etc. But definitely that's not what's happening. So I try to say using computation alone, even just in terms of processing power, is not enough. And also, other thing is I want to say the algorithm have not quite reached the human level of intelligence for complex tasks. Okay, so the question, okay, will you trust the computer to be the jury to decide if one person is guilty or innocent? Will you trust it?
Yes.
Yeah. Okay. So actually, I think probably a computer might do a better job in many cases, but the problem is, will you actually convince other people who doesn't understand how the program works to believe the results? Similarly, say if you go to a doctor, instead of the doctor to give you a prescription, the computer program give you a prescription, say you have to go to, and even in worst case, you have to go to surgery. Would you trust it? It might be better prediction. Say the result shows that some data one algorithm is better decide which subtype of cancer is you get better than the actual doctor, but would actually trust it. That's the thing. Okay, so because these are what I call complex tasks, you really need domain knowledge to do it. But but for the average person, you need to understand how the model you produce from this program or algorithm to have some kind of trust in the algorithm itself. Okay, and this is some fairly old data I find out when I'm preparing this. So in terms of computational power, the computer is actually still some distance compared to human brain. So, okay, it turns out not so great. But I think everyone here heard of Moore's law, yeah. And this is fairly old data. You can see it just stopped at around about 2000, and this is the processor and the computation power, and its growth over time. So it's more or less follow a straight line, and which is Moore's law. And there's some projection there, the green part at the top right corner. Okay, so you can see, if you look at the middle line, this prediction is by 2020. I mean, the single processor computation power will be about equivalent of a human brain. That's the prediction. Or even maybe 2030, it depends. So currently, even in terms of how fast you can compute, in theory, and human is still better. Okay, so now I come to visual analytics. And the whole idea of visual analytics is to combine the strengths of human and computers. So these are two completely different things. They build around them completely different fundamentals. Human stuff, organic. It's kind of natural. It's kind of based on a random base. But computer is very rigid. It's either 0 or 1. There's nothing in between. You can't really do random things. We'll come to that. So computer is very good at remember things. You can store large amount of data. They never forget, unless the hard disk broke. And very fast computation compared to people. But really, this is numerical computation. Okay, everything you can reduce to addition, and you can use computer. So this includes multiplication, exponential things, or even more fancy ones like regression or clustering. Okay, so computer is really not so good at anything random. So you probably know there's no real random number generators in computers because you can't do. So people now think, okay, maybe you can use quantum computer to generate random numbers, but just to show, this is something particularly computer is not good at. Okay, so if you look at human, compared to computer, we're terrible at remember things. So our working memory is about maybe 5 to 9 digits on every 7 digits. So you can remember 7 numbers in your working memory, hold very slow in terms of computation numerically. Okay, but what we are good is very good at visually picking out complex patterns. not all of them, specific type ones, and these, and so it's kind of like a result of evolution over a very, very long time. We have to survive, so we have to be have very fast response to certain patterns that we see visually. And as a result, we have this. And to show some of the examples, and these things are called the pre-attentive visual patterns. And these are things you will recognize immediately. You don't have to process use your brain. So it's kind of, you see it, you already find it already. And so, for example, this one, you will see the green dots immediately. So the color is a pre-attentive pattern. And we'll see a few more examples. It's the same thing. So we'll show you a number of items. One of them is different from the rest. Some you can see very quickly, others you can't. You can see this one. So orientation is also works. So we somehow train to see this kind of thing very quickly. Motion is another one. You can see that dots moving. Size, yeah, okay. Otherwise you go back. And this one, shading. And finally, this one. Okay, so it's a bit longer, okay. There was a difference between milliseconds and seconds. So this is the one, so it's the compound vision, so you can probably all see by now, so you got something here, which is different. But this is something we're not really trained to. It doesn't just show up immediately. So we'll come back to this later, but one of the ideas when you try to visualize data, you have to design the visualization to the way for easier for humans to pick up these patterns. Okay, so come back to visual analytics. That's a little bit like a diversion. And so in here, the visualization is a glue, which you stick together and the algorithms or the data and with human. So it's a medium of semi-automated analytical process. And so if we say, if you just run a clustering algorithm on a data, I would say that's fully automatic. And not much maybe, you have to set up the parameters or pick the algorithms at the beginning, but the whole process itself is almost fully automatic. And we'll see some examples like how can you do this like semi-automatically. Okay, so human compute machines cooperate using respective things paperless for the most effective results. So basically, let human do what human good at, let computer do what computer good at, and combine that. And finally, and users or humans should always have the ultimate authority to decide okay whether that's something useful or not. We'll come back to that later. Okay, so if we try to put kind of the theory or the concept and in a diagram, and we can have two pathways, and the top one, I call it computation pathway. You have some data, you do mining, including pre-processing, and you generate some results, or maybe you train your model, and you can use that to analyze or predict the next data. And you generate some hypothesis, and finally, you get some knowledge. And the bottom one is what I call visualization pathway. Again, you start with data, but instead of doing algorithm, you try to create a mapping from, say, abstract data to a model. And sometimes it's fairly natural. You can put everything on a map. It's very easy. And sometimes you can do more crazy things if the data itself doesn't really have a geometry. For example, if you look at Twitter data, itself doesn't have a geometry. You can map it whatever way you want. You can look at the picture, visualization, you find some patterns, and you also generate hypotheses which leads to some knowledge. And really, so what visual analytics try to do is to combine these two. So it always starts with data, and you can do both, and either visualization or computation. You've got models, and which might depends on what you can find. The patterns might lead to some knowledge. And so the only part that's different is actually the middle. So you have a little bit of interaction between the visualization and the models, which I'll explain a little bit more. Okay, so if we look just like model building, and you probably do this already, and you can steer model building with visual findings. And very typical thing when people say you are given a very big set of data, the first thing you want to do is find out roughly what is in the data, and then decide what method you want to use to apply it to this model. So to the data to find what you need. And as if you can do more visualization to understand better about the data set, you can better choose your model, your parameters, etc. Okay, you can do parameter refinement. So interact with the automatic methods by modifying parameters or algorithms. And okay, so this is, I guess, currently most commonly is okay when you try an algorithm in the first parameter setting doesn't work. Usually it will not work so well in the first run. You go back, change some meetings, just go back to see how good the result is. Is that improved or actually make it worse? And you go back until you're quite happy with the result. And actually you could do that interactively. So there's algorithm which will give you real-time feedback as you change the parameters early in the run. Okay, and you can also do model visualization. So it means visualize the resulting models to help users better understand and build trust of your methods. So this comes back to the saying, you trust the computer to be the jury or the judge. So if you can visualize the model that your say the classification algorithm, and which if you give input, it gives you an output either guilty or innocent. And if you can explain that model better to the person using visualization, people actually would understand how the model works and maybe build trust, or even help, say, the user to improve the model itself. Depends on what the roles were there. Okay, so now I'm going back a little bit in time to show a very brief say history of how visualization developed over the times, and this will help us to understand, okay, what the visual analysis is different from, say, the visualizations people made, say, 100 or 200 years ago. And anyone seen this before? Good. There's a few people. Here you can see a little bit of the text. Anyone want to guess? Who haven't seen this before, what it is? So it looks like a map. Yeah. And I guess so. Maybe there's some year. Yeah, there's some year in the first line of text. Anyone can see Moscow if you have really good eyesight. There's Moscow there. Okay, so this is a visualization someone made in 1869 about Napoleon's invasion to Russia in 1812. So it was winter. So obviously that's a disaster for Napoleon. So what we visualize is, so the line is the path Napoleon's troops took, and the width of the line is how many troops he had at the time. So you can see this is where the whole march starts. So very slick line. And its progress, we have kind of diversions here. Some troops go there, some troops go there, and you go all the way. And as it goes along, the line becomes smaller and thinner, and you can lose troops on the way. And until here you get Moscow, and then decide they're going to retreat. On the way back, and then even more troops lose. And this is what he got left when he get back to Paris. Or not really Paris, that's the border between France and Russia. Okay. So this is really a very early visualization made in 1869, purely done manually, but it gives you a very good overview of what's happening. Say you might need several pages to describe the whole invasion of Napoleon over these times, but this gives you a very quick view of that and very clear, much better. Also, there's a little bit thing. So there's a line chart at the bottom which actually shows the temperature at that time. So you can see, and these are the main events. These lines shows which are the main events happens. But I can't really read them. I think it's actually in French. Okay, I think most of you would have seen this before, isn't it? Maybe I should put that one across. Anyone haven't seen it? Oh, okay, brave people, very good. Okay, so the reason I put it behind is, okay, this is made slightly late events. But 1854, there's a cholera outbreak in London, and someone tried to find out, okay, what's the source of the outbreak. So they plot every patient which is sick on the map. So each dot is a person who is reported to be sick. And you probably can recognize this is quite close to UCL. right? So you have a Regent Street there, Oxford Street on top, isn't it? And I don't really know where Dean Street is, but anyway, so you should be really familiar with the area. Okay, so the conclusion is, you can see it's quite dense, but lots of dots in the middle, right? And there's kind of reduced. So basically there's a well there, the water is contaminated, which is the source of the correlate. So that's what it is. So I guess this is one of the very commonly used examples to show, okay, how do you visualize your data? And these kind of patterns, okay, it's quite dense in the middle, and there's a well there. These kind of patterns you can visually pick up. And it will be actually much easier than you look at all these reports, okay, this person at this street number here, which is sick. Very honest, much easier to spot this kind of pattern. Okay, so we jump ahead, say, more than 100 years, and this is now coming into the computer age, and you can have automatically generated visualizations. And the very first type of visualization is mainly used to confirmatory data analysis. Okay, so it's using visualization to present results, which you haven't seen many times. I think everyone using Excel to produce bar chart at some time during their life, and you can do different charts. Okay, and the only thing I want to say here is, at this stage, really you want to report something you find. And sometimes it's easier to find using graphics because it's easier for other people to understand. So that's the only purpose for visualization at that time. And from 1977, when computer becomes a little bit faster and can actually start doing interactive things, because previously the graphics is very poor and speed is just too slow to do anything interactive. And so there's like a landmark book by John Tuckey, which is a professor in statistics. He wrote this book in 1977, and something called exploratory data analysis. And the main difference from previous stages, you can actually start interacting with the visualization to find out more about the data. And this is one of the very typical work from his, one of probably most famous work from Professor Tuckey. And this is, they call it small multiples, but this is basically the projection of high-dimensional data. So we can, let me see. Okay, so if you have high-dimensional data, you can always project to two dimensions, and there's lots of methods to tell you, okay, which are the two best dimensions to project, so you can keep, say, best preserve the distance between the nodes, between the data points, etc. But here, and instead of you pick, it shows you all possible projections you can have. Okay, so imagine you have, this is the 5-dimensional data, and say, let's say, sorry, this is 6. Okay, so in the vertical you have, and say the first row, it means the x-axis is dimension 1, and the second row is x dimension is 2, and third row is x dimension is dimension 3, etc., etc. You have 6 dimensions here, and on the column-wise, each column is representing each dimension as well. So, for example, this shows you project your 6-dimensional data into a 2D dimension, which x dimension is the 6th dimension and the y dimension is the 1st dimension. So you can actually see, so all different projections of this high-dimensional data, and you can actually interact with that as well. Okay, so that's one of the things, typical things. And at about year 2000, and so there's some new terms come up called the visual data mining. And this is some stage when we actually integrate data mining algorithms with interactive visualization. So this is show one of the examples. Are you all familiar with association rules? Yeah. And so really, this is the visualization of all possible association rules you can get from a data set. So basically, for example, these are your product types. You say cereal, cookies, etc. Sorry?
We will talk about it.
Oh, okay. But basically, association rules just give you the idea, okay? And if someone goes to the supermarket, where do they always buy and BA and peanut together. If they always do that, higher than say a random chance, we say there's an association between these two items. And this is because if you have n items in a supermarket, you can have n squared association rules, and it's quite difficult. Okay, sometimes you have to pick, okay, which one of these n squared rules is important, and this is just to give you a visualization to say, okay, how strong these two items are correlated, depends on association rule computation.
Excuse me, it sounds like a fancy term for correlation matrix.
Yeah, could be. Yeah.
But it's the correlation, the height of the
yeah, the height of the bars
right?
indicates
Okay.
how much correlated they are. Okay, if we move on further on, say in 2004, then there's first someone made up the term called visual analytics, and so this obviously a very young field, and also something interesting about it, say the starting of the field is it actually started by someone write a book to say what this field should be about and what are the problems should be studied in this field without any answers, of course. So I don't think any other field is starting this way. This is quite unique. And at that time, it has a very strong focus as well. So this is just after the 9/11 attack in 2004, and the Department of Homeland Security in the US is very interested in visualization to understand better the data they have. And they wanted some tools when they picked visualization, and that was a very strong focus at that time. And this gives you some kind of, okay, if you need a formal definition, someone say, and visual analytics in that analytical reasoning facilitated by interactive visualization. But how is that different from previous visualizations? Okay, so you can already make visualizations long time ago, and you can do interactive. You combine with data mining. And I think the difference is actually to make sense of big data, so the data volume is larger, and support decision making. And support decision making is something kind of lacking before. And say, okay, for example, you can generate all different charts of your sales reports or your inventory or your customer relationship data, different visualizations. But from the data you have to the decision you make, okay, say, should I just keep this should I say keep promoting this new product, or should I shut down this is not performing well? Should I is anything performing good or not good enough? So basically, between the data you can see and the final decision you make, these are like a business decisions, there's still quite a big gaps there, which wasn't quite covered before using visualization. And this is something visual analytics try to support. Does that make sense? Or hopefully. Because I wouldn't really quite show you any good example yet, because it's actually quite a hard problem. Okay, some comments or notes about visual analytics. So it's relatively new, and compared to other fields, even compared to information retrieval, it's really young and very challenging problems. And most of the reason people turn to visual analytics is because many of these can't really be dealt with existing approaches, and you need a different way of thinking. Okay, how can I address that problem? And can't 100% rely on computers, and also potentially have very big social economical impact. And again, say there's lots of open problems, and there's principles and general approaches, but really, in many cases, the solutions are not quite there yet. So we still don't really have a good idea of in general, how do you visualize very big data sets. There just isn't. And actually, the main limitation, say, for visualizing a very big data set is not the computer. You can build a very fast computer. You can build very large display with, say, maybe billions of pixels. But there is really the human. Say, if you look at that picture, can you get anything out of it? If you can't, then not much point, even you can display all the data. Okay, so the hard part is actually the human part. So it's not just that hardware is not there yet. Okay, so going to show you, say, a video, which is kind of a made-up scenario or user case, how people are using visual analytics to detect and say epidemic outbreak. So I think this might give you more, say, concrete or tangible idea of what a visual analytics might look like. So is it? Okay, I'll skip a bit more. Okay, still great.
Banks serve billions of credit card transactions per day. They have to quickly detect and share their own database of hospitals concerned by the disease. Imagine the epidemiologists with visual to understand representations of their results for communication. Let's now imagine the epidemiologists with visual analytics capabilities. Here we have an epidemic that touches 4 countries with an abnormal hospital admission rate for people with the same symptoms. They can share their own database of hospitals concerned by the disease and visualize them on a map. It looks like it is not contagious, but experts need further exploration to identify the causes and the nature of the epidemic. After hospitals, a new idea is to share and visualize the localization of people concerned by the disease. Looking at the propagation of the illness, we can see that the pattern doesn't follow communication axes or circle waves. This is a specific pattern that has grown and stopped abruptly. The experts therefore conclude that it is not a contagious disease, but most probably a food poisoning. So epidemiologists decide to investigate what kind of products all of the patients have ingested and localize them on the map. First thing to do, identify the 3 supermarkets closest to these people. Now, with a list of the supermarkets that might be involved, they can immediately take a look at all the products most of them have in common. This time, the list of products is too broad, and they immediately know that they have to try something else. The experts then try examining the local suppliers and distributors. This time, it's manageable. They now have to check if something has changed for these suppliers during the last 3 months. The epidemiologists have found 4 possible causes for the outbreak in record time. The next steps are preparing a preliminary report for the press and for the medical authorities by extracting some of the visualizations they used. Then they can investigate the 4 possibilities to find out if one is the cause or not.
Okay, I'll stop there. But I hope that gives you like a more concrete idea of what might be a case of actually people using visual analytics to solve some real world problems. And you can see in this example actually the visualization itself is not very fancy. You probably can build or see better ones than before. But really the tools there is actually support all these and so-called epidemiologists to making decisions based on data to find the cause of your what's the possible cause of this, and say first I have to identify whether that's a food poisoning or a different, say, airborne disease, and what might be the possible cause, and generate cause afterwards. So that's part of the decision-making process that visual analytics try to support. And but you can also see, say, visual analytics is also touching on, say, how do you collaborate between different users, and also how you using these new type of user interface like big power wall, basically lots of tiled together monitors, etc. And okay, so I mentioned earlier, say, visual analytics is really an intersection of many different areas. So these are the ones which is core to the field. So at the center is visualization. We have seen quite a few already, and right next to it, there's spatial temporal data analysis. I don't know how much we'll be touching in this course. And besides in computer science, actually it's used in lots of other, and say, maybe you should say disciplines as well, say geology, astronomy, and even climate or biology is used a lot. But definitely used a lot here in visual analysis as well. And it's also important in terms of human perception and cognition. So I showed you a very simple example at the beginning. So these are pre-entitative patterns that you can see, and these are definitely the work from the cognition side. And we will look at data management and data mining later on in more details. And you definitely need proper infrastructure and can support all these. And ideally, like the one just showed in the video, and the visualization. Finally, is evaluation, and it's actually very difficult. Say if you have algorithm, it's very easy, and say in most of the information retrieval algorithm will have standard benchmark data. You can have standard measurement, precision recall, or F measurement, etc. But okay, if you want to measure, say how the tools help people making decisions, that's very difficult. It's not like the difference between 0.25 and 0.27, and whether you can say that's statistical significance or not. And so doing evaluation of any method is actually quite difficult scientifically. Okay, so next let's look at visual analytics and data management. And so this is kind of going back to the big data thing again. So the current data management is mostly built on relational technology. So you're familiar with, say, so it's actually built on quite old research. So the paper by Ted Court in 1970, relational model. But you definitely learn the relational model one way or another if you haven't heard of the paper. And at that time, they produced something called System R and SQL language for that system. So that's essentially the base of all existing and relational database. Very mature and popular, and they have these nice features called ACID. Yeah. So ACID is really designed for transactions. So you want to, okay, if anything wrong with the transaction, you can always roll back. If it goes wrong, it won't affect anything else, any other transactions. These are all very important for banks when they say do the transactions, so people say we can pay money, etc. And almost every organization will run one relational database in one form or another. Okay, the problem is, so these are not ideals for semi-structured or unstructured data. So examples include emails, documents, tweets, images, videos, etc. And actually, in some sense, the data in these formats actually are more than those relational data or structured data. But really, the relational model was built for structured data or relational data, and really built not for these things. And typically, it's actually not really ideal for high-dimensional data. So you can, and in the real world, you can easily have, say, data with hundreds or thousands or even more dimensions. An example from information retrieval is if you treat every single word as a dimension, you can easily have thousands of dimensions for your data. And really, this is not ideal for, say, relational database. Okay, so the trend is no SQL. Anyone heard of Good. And I think you probably will learn more and more of these in the course anyway. And these are really, okay, it doesn't say it's not SQL, it's saying not only SQL. So they do still consider SQL type of data. And they do not really based on the relational model anymore. And as a result, the query language is not necessarily SQL. Okay, they are not perfect. They are not, say, better than SQL in, say, every way, not really. They optimize for retrieval and appending. And so they assume the data is only growing and the data doesn't change that much over time. That's the assumption. And it's really not for transactions. They do not even say, most of them don't guarantee the ACID property. So you can't use that to handle transactions, which will cause disaster. And again, say the focus is on performance and scalability, and especially for unstructured data. And these are some examples. So I think in the last speaker mentioned some, in one slide mentioned the CouchDB, or CrunchDB is one of these non-SQL databases. And these are built for different type of data specifically in mind. And so there's MongoDB, which is designed specifically for documents, and Neo4j is for graphs. These are the typical data types which relational database can't really handle well. And okay, so last week also mentioned the key value pairs. And the example I put there is Cassandra. Anyone heard of this? Yeah, it's actually made by Facebook. That's how they manage their data. And they made it open source now as a Apache project. So these are different types of technology started emerging. There's lots of them actually. And I'm sure you've heard of Hadoop, yeah? And probably most famous technology associated with big data. But it actually is not a database really. So I just want to say it's not a database, it's a file system designed to work with, say, MapReduce, which you will probably learn in this module, which is how do you distribute your computation say instead of running on a single computer, it is designed to run on multiple computers. It's actually a very, very hard problem. Okay, yeah. So far, I talked about in terms of data management. It's not really, say, the core research area in visual analytics, but it's essential if you want to handle big data. And these are some of the attempts people want to actually visualize very, very large data sets. And these are the results. Okay, so I already mentioned the biggest limitation in visualization is human, because the amount of data you can go through the human and you can understand is very limited. We're good at pick up patterns in the higher level, but not the details. And the next limitation is actually display. So if you have a screen, the most number of data items you can display is the number of pixels on the display, okay? And if one pixel is one data, that's all you can do. You can't display any more, literally, because they will cover some other data. And this is exactly what this one did. This method tried to maximize the number of data items you can display on the screen, but still try to show some patterns. You already can see some patterns, but you don't quite understand what they mean, which I'll explain. So here, each data record is a pixel, and each square is for one attribute. And so again, this is 6-dimensional data, and this square is showing the value of one dimensional or one attribute, which will explain what that is. And this is the second dimension, third, fourth, etc. Okay, so this one, which we'll look at, is the days of hospitalization. So how many days a patient stayed in the hospital. So obviously this is medical related data. So color indicates the attribute values. So the darker the color, that means less the value. So you can see that on the edge is darker, and in the middle it's quite bright. That means people stayed a long time. Okay, so the next part is actually the records, or these pixels, are ordered by the patient age. Okay, so there's some ordering in terms of how you display them, starting in the upper left corner and spiraling into the center. So the way the data ordered is, okay, I use this one. Start this way, okay, and that's the one with the least value and goes on, and all the way up to the middle. So at least you can see some very obvious patterns for the first one. The younger patient has fewer hospitalization days, and compare to the older patterns, because these dots are ordered according to their age, and the color indicates how long they stay. So the first one is relatively trivial example, but you can see the other ones also show some kind of pattern, what you can see out of data. But these are not as clear as the first one. But usually these ones are probably the more interesting ones. For these ones, you probably can make a guess. You probably already know, you just need to confirm, and you can just do some query or statistics summary on the data to get the results. These actually more tell you something more interesting, because they are not so straightforward. Okay, and this is a part which is related to data management, but also visualization. And first I want to kind of clarify what I meant by data reduction and abstraction. So here basically means to obtain summary statistics. And initially this is mainly to estimate query cost in a query optimizer, say. And basically if you give a database a query, say I want to select counter star from a certain table, and this is a very simple one. So usually the query engine or database will go straight and do the query. But say if you want to do a join in two tables, or the tables are very big, the query, so the smart database engine will come up a few different ways to do the query and compare their cost and pick up the one which do, well, say take the least time or the least memory to do that. And they need the data reduction summary statics to do these things. Okay, and in these cases, the precision is usually sacrificed and to achieve speed, but they're usually adequate and much cheaper than the full evaluation. Okay, and recently these started to focus on the OLAP application and data warehouse, which we'll talk about later on. Anyone heard of OLAP and data warehouse? Yeah, these are, actually not that new technology anymore. Okay, so something related is visual data reduction, and when you visualize lots of data, large amount of data, you have visual problems, and you can have clutters in the image when you have large amount of, you have lots of dimensions, and then you will also have performance problems. You want to have an interactive response time. Usually that means no more than a few seconds. And so these are the common problems you have when you try to do visual data reduction. And you require new technique and also new data structures and algorithms to do that. Existing techniques, you can do sampling, which is quite a dumb method. And it's the simplest one is random sampling. And you do that to reduce your data size. And density-based hierarchical data aggregation, slightly smarter. You first have to compute the density of the data, say a distribution over a certain dimension, and say depends on the density. You not do random sampling, but okay, if it's a very dense, okay, if a certain value interval is has lots of data points in it, you sample more in those area in that interval, and if you've got less points, you do less sampling, and you do this hierarchically. Multi-resolution is a fairly similar idea, but really common understanding of how to interactively visualize these data doesn't really exist. And so, okay, currently, and if you want to reduce visual data clutter, and you usually use something called the quality matrix to measure how good the visualization was and how good the result is. And so you can't optimize for everything, so you have to pick up, okay, depends on what you want to do, and pick some of these metrics. And so similar, okay, so very simple type of metrics. You can always measure size, how many items you want to visualize, and you can measure how effective the visualization is by saying, okay, how dense the data are. So usually too dense is not good because you start to have occlusion problems, so you can't see the data points, which you should. And there's other ways which you can actually measure how much the visualization preserves some certain features you want. Okay, so these features, okay, if you have clustering in the original data, you want to preserve that. On the other side, you may have outliers you want to preserve. You may want to preserve relative distance between data points, etc. These are different things you want to preserve. Okay, this is one of the work to try to do this in a visual analytics way. So it has very specific goal. It's want to discover and preserve data density difference. So that's the thing you want to show. And even after, say, reducing the amount of data, you want to visually keep the data density difference as much as what they were in the original data. And it used quite a few metrics to do that. And I'm not going to go into details, but these are the ones listed on the right. So you can see on the left, these are two images, one before and after reduction. On the right-hand side, actually, it's give you a list of measurements and what their values are after the evaluation. So these actually are the comparisons to show, okay, for this measure, after reduction, it's actually reduced, but some measure actually improved, become green. So these kind of interactive way to how to decide what's the best way to do a visual data reduction based on your algorithm. So basically, you tune your parameters to achieve, okay, what you want to see in the results, and say remove, and at the same time, say for example, remove as much data as you can. Okay, so next time I'm going to move on to data warehouse and OLAP, which I already mentioned a little bit. So before explaining what they are, or compare that to relational database, and I want to mention these share some common goals of visual analytics. And so they're really designed to support strategic analysis and decision making. They are not designed to provide you with the most accurate data. And they are not designed for transactions. Again, not for asset, property, etc. Okay, so what's the difference between data warehouse and relational database besides they're not designed for transactions? So they integrate data from many sources. So essentially, this is a data integration problem. And usually, if you make a decision, you need data from many different sources, so different departments, different type of data. And just to put everything into a single data source is actually quite a difficult problem. And it maintains data history. So for example, and your sales figures changes over time, but data warehouse will keep all the previous numbers, what the numbers were, say 2 years ago, 1 month ago, or 1 day ago. And this is sometimes called problems. Okay, and this is probably the most interesting thing. Say data warehouse, you try to aggregate data along different dimensions. Dimensions here means time, location, product to support decision making. And partly because it knows, okay, you usually use these dimensions to say, you usually break down your cells according to time or according to the area, which is location. And so you know this, but also because usually the data is very large, you can't really do this in real time, in runtime. So you have to do pre-aggregate, pre-compute to have aggregate the results stored in the data warehouse to do these. And these again is sacrificing the precision of the data and trade for speed. So aggregate the results obviously not as accurate as the details, but certainly because pre-computed is very fast and reduce the amount of data you need to see. Okay, so let's say the data warehouse is the back end and the OLAP is the front end, so where the user actually use it to query the data warehouse. So very typically, you will heard of data cube if you heard of data warehouse. So data cube is a set of multi-dimensional data. Just like the cube, we have 3 dimensions. It can be, say, time, location, sales value, etc. But this one, in theory, a data cube can have much more than 3 dimensions. And you have these operations to do and can operate on your data cube. And you can look at higher level aggregation results, which is raw. You can go look at details, drill down, can slice and dice. So you just want to set the year or set the location and look at that value. Okay, so all that was like a very, very long introduction to what people currently doing in terms of visual doing all that. This is a system called Polaris, and it's quite old, more than 10 years as the interface. And the basic idea, they try to do this OLAP analysis of the visual, the data cube visually. So I'm not going to explain what this one does. The text is too small, so instead I'm going to show you this one. So that software was from Stanford. So those people, the PhD students made it, and later on set up a company called Tableau to commercialize the whole idea. So Tableau is actually currently a very successful commercial software and commercialized visualization software, and it's designed specifically just mainly to do this visual OLAP analysis. I'm going to show a video now, see what it might look like.
Going back to how Tableau has now segmented our data, we see that it's placed all of our field names into dimensions and then segmented some into measures as well.
Okay, so very quickly, you can open anything in Tableau, and afterwards it will automatically recognize these dimensions. If you remember, you have dimensions in data warehouse. These are the locations, but it can also recognize something as measures. Anything valued and recognized as measures.
The best way to think about dimensions and measures is that measures create axes and dimensions create labels. Let's go ahead and talk about this. I'm going to drag sales out straight onto the view. And you'll see it's taken an aggregation of the total sum of sales aggregated up to the highest possible amount. We've sent a query back to our Excel spreadsheet or relational database or whatever you're connected to and returned a single result. Now, if I want to categorize this out, or cut this, or slice this, I can take a dimension like region and drag it out here. And now we've aggregated it down to the region level. Measures are those things that we want to do aggregations on or calculations on, and dimensions are the slices or the categorizers. Let's keep going with this. What if I dragged another dimension out and placed it on rows, like product category? You'll see that again, the sum of sales is now aggregated not only to region, but also to the product category. Tableau does a great job usually of reading both dimensions and measures and placing them in the appropriate section. However, once in a while, it will make a mistake. Something like order ID, toolbar menu, and below it, some one-click quicks card. The marks card, it contains additional shells like text, color, edit, the sheet. I'm going to call this getting started. And then if I wanted to create a new sheet, reiter each of the sheets. Another really easy way to get started visualizing inside of Tableau is to use the Show Me function, located here on the right-hand side. Show Me is outstanding for when you know what kind of data you want to visualize, but you're not necessarily sure what type of visualization. So in a situation where I wanted to talk about product category, product subcategory, which I can select by holding down Control in addition to product category, as well as region, and then my sales measure, you can see that Show Me is using Tableau's best data visualization practices to recommend a specific chart. Here it's got stacked bar chart outlined in blue. It's also telling me I can use horizontal bars, as well as a pie chart, or any number of these that are not grayed out. In addition, if I mouse over one that is grayed out, for a simple example, this map, it's saying that in order to use this, I need to go ahead and select a geolocation as well. Let's go ahead and use the stacked bar chart. Tableau has now placed our product category and our product subcategory dimensions on the column shelf, and then the sum of sales on the row shelf, making a bar chart. Additionally, it's taken our region dimension and placed it on color, making each single bar segmented by region. So this is great. Maybe this is exactly what I wanted. but maybe it's not. It's great to remember that the Show Me button is just a starting point, and that making a change is as easy as dragging and dropping. And now I have a region all along on each row here. Let's say I wanted to also incorporate profit somehow. If I just dragged it and dropped it right onto the view, you'll notice here that it's now automatically been placed on the color shelf, again, as a visual best practice built into Tableau. Right? We're quickly able to identify that we have a profit issue with tables in the east. You'll also notice that instead of segmented colors, visualization. So in a situation...
Okay, so I think the video gives you some kind of ideas, okay, how Tableau is doing this on OLAP visually. And really, say, when you visualize a high dimensional data, it's very limited dimension in your visual channel. So you can always use X, Y as two visual channels. And after that, you have to resort to, say, size, color, and even go to text. And then text is not quite visual already. So again, say you have fairly limited visual dimensions you can use, and how do you map that to the high dimensional data you have? Usually maybe tens, dozens, or even more. And there's something Tableau tries to do automatically and actually doing quite well. Okay, so next I'm going to talk more about in-terms challenges and opportunities. These are kind of problems people recognize, but haven't really any good work there yet. And the first one is about uncertainty. So this is about, say, issues and of incomplete, not consistent or errors in the data. And actually, and in the real world, no data is perfect. Every data will have errors or complete or incomplete, or sometimes it's kind of like a malicious data. People give you false information. And in many cases, people just ignore these. Or actually, in most of academic researches, people always assume, okay, the data given is perfect. We don't need to consider any of these problems. But these are actually very big problems for the actually users. Okay, so next one is actually called data provenance, which is something actually I'm working on as well. So provenance is related to issues like, okay, where data comes from, and what kind of analysis has been done on your data. So say if you know the data source, you have the credibility of your source. And then if you know any analysis results, you will be able to better understand why you get the result. Okay, so the picture there showing something, existing system, and it tries to record what has been done as a tree. So you start from your original data, you do different type of analysis, and the result is shown there. And actually all these itself is actually a fairly complex workflow as shown there. And the users that can actually write notes about what they did for that specific workflow, what they did. So this is to say the provenance of the data. So it tells you, for example, how do you eventually get to this visualization, pretty pictures, what data you used, what kind of analysis you used, and what's the parameter settings, and even the rationale why you did that kind of analysis. Okay, this is another picture. It's about visualizing streaming data, which is extremely popular now, or common now, say, and lots of the big data actually is streaming, say Facebook, Twitter, and even transaction data itself is streaming. And there's quite a lot of research in terms of how to handle that in terms of data management, how do you store them, how do you run constantly updated results based on new data, which are coming all the time. And this is one of the visualizations showing. Okay, this is a visualization done by the New York Times. They're actually quite good at producing visualizations. And this is showing the revenue generated by the movie. And so this is 2007, and there's one there called I'm Legend. So obviously this is when the movie first becomes available, and how that revenue generates decay or reduced over time. So this is one type of visualization you can do to do that. But really, there's still lots of work to do there. Okay, this is something quite interesting. and maybe related to the previous talk as well. I think in the last talk, and the speaker mentioned, Toby mentioned, okay, and for these senior managers in the companies, they're very good at what they do, but they're not really technically savvy people, and any complex visualization they might just disregard and don't even bother to look at it. But currently there's actually a kind of trend of people working on visual analytics for the masses. So masses here more means general public, which is not expert and in visualization, maybe doesn't even have a degree in a computer-related field. And to help them to understand their own data, or maybe even the public data. For example, UK government have this data.gov.uk website. They have lots of data there, but it's almost useless for general public. I mean, they don't even know what's there and what data means to them. So there's a general trend, okay, how do you address these problems? And the picture shows that it's something called Many Eyes. And the name is on the title bar, the blue title bar. And it's made by IBM. And the idea of Many Eyes is quite interesting. It's almost like a social network for visualization. So people can visualize, upload their data. So all you need to do is upload, for example, a CSV file, and then you can select any types of visualization available from the website, and it will generate a visualization for you. And you can write comments, but also other people can look at it, and you can publish your results. And other people can look at your visualization and leave more comments, and people can have discussions, and you can link different visualizations together. So that's one of the ways to visualize data socially.
So is there a size limit?
Sorry?
Is there a size limit for the data that you can upload from the
Yes, I think so. But I think usually it's big enough for everyday use.
I think it's all anything you can upload over an HTML interface. I don't think there are FTP uploads or anything else. So it's sort of a practical limit of the interface.
Okay.
This is not really designed for very, very large ones anyway. So these visualization techniques are really designed for quite small size of data, but useful for people to discuss. But really, what they kind of remove one obstacle for people who don't quite understand, say, computing that much. So they understand, say, how to upload the data, which can already be challenging sometimes, and pick some visualizations. Okay, I think we're running a bit ahead of time. So now I'll talk about a little bit about visual analytics and data mining. So these are mentioned already earlier on, but the benefits is actually you can, using visualization to translate users' questions into the inputs for the data mining algorithms. Sometimes this can be really difficult, and say what user really want and needed is not quite, say, you can describe using code, but how do you can kind of alleviate this problem using visualization. Now maybe I could come later. Okay, so there's some very simple example which you can direct how do you do the clustering, and you can run, say, any clustering algorithm on, say, a set of photos that will show the result, and the user can actually, say, interactively put two pictures together, whether they think these two pictures should be in the same cluster, and this information can pass back on to your clustering algorithm and will adjust its model based on the input and then change the result. So this is one of way to actually turn user input into set input for the algorithms. And as I said, you can steer model building with visual findings. So it depends on what you see in the data. You can choose what's the better parameter or better methods, and somehow incorporate expert knowledge into the data mining algorithm, and which I don't really have a good example here yet. Oh, okay. So this is just the previous one I mentioned, or it's the same example as before. So you can tell the clustering algorithms which are the two pieces of data which you think is relevant or should be close together, and so that the model can be adjusted accordingly. And hopefully by visualizing the rules or the final models the algorithm produce, you can understand it better. Okay, some applications. So these are not really detailed works, but some kind of like successful stories of applying visual analytics to different domains. And so this is one, say 10 out of 15 most cited articles in the bioinformatics journal propose visual analysis tools or methods. And does bioinformatics mean anything to you? No, okay. So one of the biggest usage of bioinformatics in genetics, say for example, you all know we sequence the entire human genome. There's lots of like a computational work there. For example, the data you get from a sequencing machine is very short, maybe 50 base pairs, so basically 50 letters, either A, C, G, T, and you have to somehow stick all these letters together to make it one human genome, because human genome is just very long sequence, and you have these and millions of very small short ones, and how do you piece it together? Other common things people do is actually just to compare, say your sequence from two persons, one is healthy, one has cancer. You want to find out, okay, which part is different, what's the variations. You can do this visually, and you can see, is that kind of all certain patterns, a sequence appear a number of times in the sequence, which you can see with this type of visualization. And another application, which is in the climate change domain, so it's not quite computer science. So the picture on the top, which doesn't quite show very well, is the distribution of fossil species around the world. And there's some computation going in the back end. And it's expert steered k-nearest neighbor prediction. So again, this is a k-nearest neighbor clustering algorithm, but it incorporates expert knowledge to do the clustering better. And you can't really see there, but this is, and something at the bottom is called parallel coordinates. Anyone heard of parallel coordinates? So it's, very common way to visualize high-dimensional data. And so typically you have XY coordinates, which are always orthogonal. Here, all the dimensions are parallel. So you have your X dimension, Y dimension, Z dimension, and maybe X1 lots of dimensions. So this way you can actually visualize many dimensions. Here maybe 20 dimensions, and each of your high dimensional points and becomes a line. So if you look at it, you can see a yellow line there. Basically, since it has one high dimensional data point. So on the first dimension, its value is quite low. Same for the second, third, fourth, the fifth is quite high, etc. So it kind of projects your high dimensional data points into a two-dimensional space, but at the cost of a line. So a point, the data point becomes a polyline in two dimensions. And this is certainly quite useful in climate change research. And so, yeah, these are some examples of applying, say, combining data mining with visualization. So these are common or basic visualization charts, scatter plots, parallel coordinates, which is shown in last slide's dendrogram, and heat maps. And these are being combined with clustering. So this shows a 3D visualization of k-means clustering results. And principal component analysis. Okay. And how the projection, how do you pick the first dimensions and how the data project onto that, or even self-organizing maps. So these are fairly standard data and fairly standard visualization techniques combined with standard and basic complete analysis, data mining analysis. Okay, another example called Viz tree, and this is designed to analyze time series patterns and try to facilitate that with human intervention. So at the top, the blue part, is the data, the input time series, and the bottom left part is the overview. You can build a hierarchical tree in terms of patterns you can find in the time series. Okay, and that panel there, this panel there, is a small region which you zoom in from here. So you might not be able to see clearly, but there's a small rectangle there actually. So this is actually showing a zooming region because this tree itself is actually very big. And this window actually shows the details, a small region which is shown there in the red. So this allows you to look at time sequence data at different scales. So, and say the blue one on top of the overview, the same for the tree here, the overview. And this is more detailed view of a small section of the data. And obviously you can zoom in and pan in, depends to select different parts of the data you're interested in. Okay, another example, called the parallel bar charts, and try to do, again, mathematical data, try to show temporal data, temporal patterns of multiple time series actually. And so you probably can already imagine, say, you have time on the x-axis, which is this way. You have your y-axis on the left, which is this way. And x-axis is time, and this one is number of time series, or time series. And z is a value. So for each time point you have a value that's there, and you can see the patterns there. And you can have, so you have like different controls of where you want to see. For example, and it shows half of the time series on the top half is shown in straight D, and the bottom half is actually flattened out. You still can guess the values just using the color, but showing straight time. And these can be changed interactively. And there's a circle there, which is basically like a control panel, where you can say even rotate the view, decide whether to show 3D or 2D, etc., etc. Okay, I think this is probably the last examples, and this is just using different visualization to show the clustering. So this is a parallel coordinates view. We already see high-dimensional parallel, and on the top part it's the same thing, and it's using the results of hierarchical clustering and using the dendrogram, so the kind of tree-like thing, and heat map, and these blue and red matrix, colored matrix, and usually I think blue is overrepresented and the red one is underrepresented. Okay, okay. Hopefully I can get through these quite quickly. So in terms of data mining, you can have predictive tasks and classification regression once you build a model, and you can analyze new data and have descriptive tasks, clustering, pattern mining, associated rules, etc. And because these are not really covered yet, so I don't go into details. But in terms of tools, you can have, which is initially mainly designed for statistics and mathematics, but they have visualization components. You can have tools mainly designed from a visualization point of view as well. Can you guess what these tools are? You probably use it already.
Left is half.
Yeah, and on the right?
Like that.
Yeah. So these are very common tools you probably use or should use. And they have some of the visualizations there. And there's the mathematics and stats, which is a similar type of tools. These are designed to be statistics and mathematics tools. And okay, if you do network visualization, which is my background, you need more specialized tools. And on the left is something called GraphViz. It's a library that can produce this type of visualization. On the right is called PyArc, which is another package which you can actually. PyArc mainly specialize in social network analysis. Anyone heard of that? So you can find who's the most influenced people in the network, say by connections, or by saying that's the person connecting two parts of the network together, even it doesn't have that many of a connection. And that's really combining those type of analysis with visualization. That's what PyArc does.
GraphViz is a JavaScript library.
Sorry?
It's JavaScript.
Yeah. Yeah. I can't really say the name. I think he's Russian. But maybe you can say better. So, okay, these are more actually initially designed as data mining tools. I think you probably all heard of Weka. Yeah, by the group at New Zealand, and probably less heard maybe rapid minor, which is this one here, is the second most well-known, and less well-known is like a 9. And 9 is developed at the University of Constance in Germany, and really it's designed for people who don't want to write code but want to build a data mining pipeline. So all these blocks are different steps you can use to build a relatively complex visualization or analysis process. And it's free and open source as well. So yeah, this is what they call professional grade open source software. So it actually is a company behind the developing software. So it's not, say, just a student or some one researcher trying to develop that. Okay, come back to this one again. So one of the challenges is towards visually controlled data mining. And so how do you include domain knowledge into your algorithms? And how do you facilitate expert which doesn't understand data mining algorithms to input and parameter tuning parameters? How to evaluate whether it actually works or not? And so hopefully visual analytics can help these things. And you can using the presentation to show the model and using more intuitive ways to input some parameters for the algorithm. And I guess the prediction is there will be a continuum from pure data mining algorithms to pure visualization. There always will be something in between, or maybe towards one extreme a little bit more. Not a single tool. Depends on your application and requirement. Okay, and finally, demo time. So first I want to show something called InVisc, which is developed at my current research group. And it stands for Interactive Visual Search and Query Environment. And you can imagine something similar to Google, but instead of presenting the results as a few lines of text, it's shown as an index card. And so this is what interface looks like. And the system is originally designed for a library, so that's where the index card metaphor comes from. And, but it really can be used for many other data as well, which we all should see. So it's working for okay. And so we have a website, just called invisc.com, and what it looks like. And if you click demos, give you a page like this, and so you have a video here, but you can actually try for yourself live here. Okay, that's a little bit dramatic. Okay, so that's really okay. So it's quite different from say the Google what you're used to, and the idea was to make it really simple, but it still needs to give you instructions. Say double click anywhere to start your search. The idea was okay, even remove that, but people will get lost. Don't know what to do with it. So you can have different sources you have to select. So this is not like Google. You search everything it can find. And I will show you some examples. Say I picked the Guardian. So Guardian providing a database of all news they collected, and this is free. You can access, and then you can. So we just previously we just tried the Prince array. You just link back, and you can see. Okay, so I guess the point is actually try to show you the interface, what the interface is like. Okay, so instead of instead of list, it's index card. Each one is a result, and it's actually ordered in certain ways. So actually the white dimension here is showing as date. So usually, so that means the higher index card, it means it's more recent. So this is the most recent one, 2013 and 23rd of January. And this is the second. And this way it's organized by title. So you can always change these. Say for example, I can organize by time and in the y dimension as well. Yeah, so the earliest one is at the very beginning. And anyone want to try another query? Okay, so there's small things here I haven't really shown yet. So you have, because you can't really see all the information, so you can have these cards which can scroll over different results. I think that allows you to show more cards. No. So you can hide that as well. Okay. Anyone wants to give me another query? What is on news now? Okay.
Israel.
Israel. Okay, there's Israel. Yeah. How do I spell? Sorry? A-E. Sure. Okay, so this is again quite different user interface. You can zoom and you can really organize these things together on your, say, we call it canvas. And we also try to do what they call Boolean operations. You know, like in Google you can say and or etc. And we do this visually. So you move this over and okay. So this is two. When there's a little bit overlap, this is and. Lots of overlap, this is or. Okay, this is. I didn't want it to end because probably there wasn't anything both Israel and Greece error. But this is give you all research results. It's a new set of results. And you have other functions here. You can. Okay, so this is actually more relevant to information retrieval. You actually do track these popular themes, which seems a number of different topics. And yeah.
Is this Flash?
Yeah, currently it's Flash, and it's much easier to put on the web page this way. And we're making a new version using Java, and mainly because of the performance issues. And also we want to use more libraries. It's less library, say, Flash to do say data binding and text analysis. Okay, so you can actually try it because it's online. You can always try it. Okay, I can go back to my laptop. Okay, this is another example. Do I have any? Okay, yeah, so a little bit of time. I'll try to do this quickly. And so this is some work I did 2 years back, and to visualize social media, and again part of the challenge. So unfortunately, I didn't win anything there. So I'll skip this part. Try to say social media is good for and visual analytics. And this challenge is called VAST. It stands for Visual Analytics Science and Technology. Basically, it's the name of a conference. And they provide you data and ask everyone to provide visualizations to answer certain questions by visualizing data. And say in 2011, you get this data, and they call microblog, essentially just Twitters, about 1 million of these, and the map. And that's everything you have. Okay, you have population statistics and weather data, because you will see why it's useful later on. And what all you need to do is to identify whether there's epidemic in the city, how it starts and how it spreads. Okay. It's not going to the next slides. Okay, so this is actually the kind of data you have. And you have an ID. So the ID is actually, I think, also ID. Time is created. You have a location, exact location of where that Twitter is posted, and some text. And of course, this is very ideal situation, but in real world, very few people actually will give you exact XY coordinates or location of that place. But some of the tweet text actually are real ones. I think it's kind of mixed, say, data. So some of these are real tweets, but they also generate some tweets, so that I can know the exact answer. So that's all the data you have. Okay. So that's some work I did. I tried to explain the interface first and then see how to run the live demo. And so that's, of course, the majority relation is just a map. And each box is a tweet text. And you can mouse over one of those to show what exactly the tweets are. You can't really see clearly, but at the bottom is a very long blue bar, which is a timeline, and which actually essentially also is a histogram of the number of tweets at that time. So actually each bar represents a few hours. And then, and on the right, you have a list of keywords, which you can't really see, but these are the keywords and which is related to epidemic, because we all know we need to find epidemic in the city. And so actually, the extracting of these keywords is quite interesting. You can run standard, say, information retrieval algorithms to find what's the popular topics or popular terms in the dataset. But then we didn't really find any good ones which tell you which of these actually are related to a disease. So I have to manually pick these, which I think is related to disease. Some examples including chest, chill, doctor, fever, etc. Some of these examples there. And these terms are color coded, so you can know, okay, for example, with this one, you got lots of pinkish color, which is headache. Using, okay, these are the tweets contain and headache in that. And finally, we have weather information, which is human. Okay, so let's see if we can get running. Well, take some time to start. Okay, it might complain very soon as well. Starting battery. That's it. Okay. Well, at least it's running yesterday. Okay. This is not ideal. Okay, so we miss, because of the resolution, we miss something here. So I have to change. Is that? Okay, hopefully that's the right one. Okay, yeah. I mean, the map is a little bit squashed, but anyway, you should get the same idea. And so you can mouse over these things to see what these people are tweeting about. Actually, see better there. And okay. And so what happens is some control here, basically just so it can allow you to play over time. So this is currently it shows on April the 30th between 0 hours and 1 o'clock. So these are 24 blocks. That's what is shown on the map, and you can play and it will just progress over time gradually. Yeah. So these time progress. Every time it shows 1 hour, etc., etc. And so, if you look at histogram here, where obviously you got lots more tweets at the close to the end, so I'm going to save you all the time watching and jump right to there. Okay. So this is May 18th between 10 and 11 in the morning. Obviously, you have lots more blocks on the tweet, and you can see these are mostly pink ones. I can hide them. Not this pink one then. This one. Okay, these are the pink ones, which all contain keyword headache, and you can have these ones, which contains fever, can't really see there's any other ones. But you can more or less guess, okay, these are the early symptoms. Okay, there's another one here, it's quite a few, which is chill. And also the other thing is when you mouse over say chill, and actually the histogram changes to of that specific word instead of the trees. So we can keep going a little bit more. So you can see, okay, there's always lots in the middle of the map, which is the city, downtown area. There's a little bit more to the right compared to other areas or suburbs. The first suspicion is because of wind. That is always a downwind area. And okay, and this you see another pattern. Have to maybe go back a tiny bit more. So keep going a bit more. Yeah, now it's going to happen. Okay. And again, so if you look at time, this is between 6 and 7, and this is when people start leaving work and go home. And it's actually all, you see all these things can start spread everywhere. And we're going to go a little bit more. Okay, and so I didn't go all the way, but okay, actually start from the 19th, the early morning of the 19th. You start to see another kind of cluster of the message around here, and you go on a little bit longer, you will see this one actually doesn't quite change. You stay there fairly stably, not like this one, not like once in the middle. And you can see the actually different set of complaints. So these are people, okay, people complaining about stomach, nausea, maybe some heartburn. So it all kind of stomach related. You can turn off some of the other ones just to clear things up. And you can see muscles start appearing, which wasn't there before, just later turn. And maybe turn off headache as well. Throat problems. Sore. And finally flu. Doctor. Okay, so I turned off something so you can see just this part more clearly. And let's keep going, it's actually, or just stay there. And so, as it turns out, on the map you can see this is actually a river going across from the top in the middle always down to the bottom left corner and to the bridge where the road cross, and some point in the water, and so that's what people in this downstream area get all pointed the fact, and they've got all these say stomach related complaints. And so the other hypothesis is, okay, some people release some, say, disease agents in the city, and it's all infect the city and the downtown area, which I just turned off. Okay, so I guess I try to say is, okay, so you have a reasonably large amount of data, about 1 million tweets, and you can see some interesting patterns just by coloring different keywords on the map. You can see what is happening over time. And these kind of things will be quite difficult if you try to figure out using any algorithm alone. And if you use visualization, it's much easier. And again, this is an iterative process. At the beginning, we don't know which keywords to look at and what time to look at. And once you have visualization, you have better ideas where to find these in your data. And you can kind of focus on a certain part of the data rather than look at every of them. Okay, I think that's all. This is my last slide. Okay, thank you. Okay.
Sorry, what's the written data visualization library that you know in Java, JavaScript, C++, whatever.
Okay. So I personally write code in Java. I know the lots there. There's some library in C++ as well, but these are more from the computer graphics community. So people do 3D rendering. They are usually more start with C and stay in that field as well. And there's quite a few JavaScript library as well. And it's much more accessible to the general public. It's much easier to distribute your work online in that sense.
And which one is the richer data visual? You know, the one that has the most visualization options.
Okay. Okay. So there's no single one which is the best. It really isn't. Yes. So fortunately, in terms of the online, so D3J is probably the best one. Why it's not showing the picture? Okay. So these are the visualizations which is already made there. You can just use this library.
Could you switch to the projector? Here's the
Okay. Sorry. Okay, so the only thing I want to mention is D3 is SVG based, and it has advantages or disadvantages. It really depends whether that suits you. And so I personally would also go for okay, so maybe Google is still better. Yeah, okay. So this is on GitHub, and this is canvas based. Again, so canvas has more flexibility, more control, but sometimes slightly more difficult coding. In terms of Java, it's quite difficult to say. Usually what you use are libraries, because it's Java, then if you do graph network visualization, you go for those. And then if you want to just do simple charts, you have very simple ones, actually not too hard for us to do Excel. Okay, I should mention this. This is actually what I'm mostly using. It's called Precision. Okay, so it's kind of like a library for Java, but actually designed for people who don't have programming background to make visualization in Java. So it's actually quite easy to use. But on the other side, it's still Java, so you can use all the Java libraries anyway. So these are actually examples made by processing. You can see it's actually very good looking. Yeah. Anyway, yeah. Okay. So that was another question.
Yeah. So if you guys interested in visualization, I think we should be able to come with a project, thesis project for you guys. So kind of I started to think about the project, which we want to build some visualization facility on top of Google, right? So it's like, you know, turn Google into not precision driven, but recall driven search. So you guys should please talk about it. Okay.
Yeah, that's a very good question.
Sorry. Do you recommend any software that runs on top of Hadoop? Visualization software.
Okay, first, I personally would not recommend Hadoop. Hadoop itself is really, say, designed as batch processing. It's not actually particularly fast. It's really, okay, you design all your work, you write your script, and let it run overnight and come back tomorrow morning. And in terms of interactive visualization, that is not really the way to go either. So there's something I was going to look at, but I haven't got a chance yet. There's something called Spark. What's the best word? So Is this the one? No. Okay, so that's something, and which is similar. Okay, and this is a home page. This is what they show in terms of number of iterations. So they're comparing Spark to Hadoop, which is always very hard. But at least I heard it's quite. I mean, in terms of response time, better than Hadoop.
Alright, as addition to
Yeah, it's definitely distributed file system, or not quite accurate.
Cheers.
Okay, great. Yeah, let's give it kind of. So next week we're going to talk about the evaluation.